So let's get into the mathematics of the fast inverse square root algorithm. Now, if you haven't worked in any mathematics involving floating point numbers and floating point arithmetic, it's going to seem a little bit strange to you at first, but it isn't actually that difficult. You just have to take your time to understand each and every term and each and every line of the mathematics. The hardest thing usually in mathematics is to get an overall picture, so I'm hoping to give you that overall picture here within this video as well as the details. Now we're going to work on a 32-bit floating point number as opposed to a 16-bit. The reason for doing that is that the original algorithm was generated with a 32-bit floating point number in mind. But the mathematics here is generalized enough so that it will work with 16-bit, 64-bit, 128-bit, or whatever value of floating point number you happen to want to use. So the basic idea here is that if we have, for example, this floating point number here, so this is actually the number 4 in floating point land. Now we know that the first bit is the sign, it tells us it's positive. The next 8 bits here are going to be the exponent. So rather than the 16-bit version is going to have a 5-bit exponent, and the 32-bit version of a floating point is going to have an 8-bit exponent, okay, and it's going to have a 23-bit mantissa. So this number here is the exponent, and it tells us the range. So it tells us whereabouts in the number line we are. In effect, it kind of tells us if we're between 1 and 2, 2 and 4, 4 and 8, 8 and 16, 16 and 32, and so on and so forth. Now, the next part here is the 23-bit mantissa, and the 23-bit mantissa tells us exactly where we are within that range. So that gives us the precision. So if we're in the range, say 4 to 8, then this number here will tell us exactly where we are within that range 4 to 8. So we talked about that in the last video, and we don't want to get into any more detail on it. Now, we're going to look at this here, and the interesting thing is that we're not going to talk through the mathematics necessarily in the way that the mathematics was originally generated, okay? I think it's actually easier to understand this if we talk through in this different kind of route that I'm going to go through now. So we know we can generate the decimal number for this by using this little equation here. So that's going to change the binary number here, and it's going to change it into a decimal value, and we know it's going to give us the value of 4.0. okay, so this is the decimal representation of this 32-bit floating point number. Now we're going to do something that's rather strange. We're going to then look at this number here, and we're going to interpret it as an actual integer. So if we start from the far right here, this would be 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, and so on and so forth all the way up here. And at this point here, this one here would be our 2 to the 24, well actually 2 to the 23 because it starts off at 0, so that would be 2 to the 23, and then we would have these zeros here, and this would be another value, okay? So we're just changing it into an integer value using a normal binary representation. So that's going to give us another number here, and we'll call that number ix, so I is for integer, and that number is 10821304332. So you look at this here and can say, well, this is all a bit random. There's not really any connection between this number 4 and this other representation here. And the question obviously is, why bother doing this in the first place? Well, we'll see that as we work through the video. So when we look at this initially, there's no connection between this 4 and this number here. This number here in effect is really just very random. We've just decided to take this floating point number and then interpret it as a an integer version of a binary number. So it seems really a rather silly thing to do. So the question then is there a connection between this decimal number 4 and this integer representation here, which is this number here? Now, in order to answer that, we're going to have to go through a little bit of mathematics. So the first thing we're going to do is we're going to represent this number ix, but we're going to represent it in terms of some of the terms within this floating point representation. So let's go ahead and we'll do that now. So what we could do, if you think about an example here, so let's say we had the number 0111. So in binary, and the actual decimal value of this binary number is going to be 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So that's going to be the value of 2 plus 4 plus 8. So 2 plus 4 plus 8 is a value of 14. But we can actually write this in a different format. We could say, well, let's say this is actually a floating point number. So in the floating point representation, we could say, well, let's say there's a full stop here or a dot here. So we'll put a little dot here, okay? So everything left of the dot is an exponent, and everything right of it is a mantissa. So we can say this here, we can interpret this here as actually a float point with an exponent and a mantissa, the same as we've got up here. Now we just ignore the sign for the moment. Everything we're dealing here with is going to be positive numbers, okay? So it means that we can actually rewrite this or find this value of 14, and we can find it in terms of this exponent. So this exponent value is a value of 3, okay? So 1 is a value of 3. And then the mantissa is going to be a value of the value 2. So we could look at this here as the number 2. Now, in order to get the actual value of 14, we note that this number here, 3, is actually shifted along, okay? It's shifted along 2 positions. So it's shifted along position number 1 and position number 2. So in effect, it's shifted along to the position 2 to the power of 2. And you can see that 2 to the power of 2 is 4. So that position there, although we interpreted it here in the exponent as just the number 3, that position there is actually position number 4. So if we take the 3 and we multiply it by the 2 to the power of 2 and they add the 2, we get a value of 14. So we can interpret this here in this form. Now, you have to really take your time to have a little look at that yourself and think these values through for yourself. Try a different value, okay? So rather than you using 1111, you could put in different values and you could generate the same process here just with different values, just to convince yourself that this is in effect true and it does work. So this is a little motivation for the mathematics. So let's now take this here and we can generate the mathematics from it. So we know we're going to call the integer value ix. So the integer value ix is going to equal now the large ex just says it's the integer value of the exponent, okay? And then we're going to have over here an integer value for the mantissa. So in this case here, the integer value for the exponent is the value 3. The integer value for the mantissa, again in this example here, is the number 2. And then the 2 to the power of 2 here is the value here that we call L. Okay, so L is 2 raised to the power of how many digits that the mantissa has. Now in this case here, the mantissa has got 2 digits, okay? So that in this instance was 2 to the power of 2. So in general, we can write ix is equal to the integer value of the exponent times this value L plus the integer value of the mantissa. So don't get lost in the words here. Just look at this little equation here, because there's a simple little equation, and equate it to each of the terms here. And then convince yourself that this does actually work by putting in a few different binary numbers and testing it out. Now, if we were to look at this thing here, we can actually do something else with this integer value of the number for the mantissa. We can actually rewrite it in terms of, rather the integer value for the mantissa, we can actually write it in terms of the actual mantissa number times this value of L. So let's have a look, and we can do that now. So let's say in this example above, the actual value for this mantissa is this, after the point here, that's going to represent 1 upon 2. Okay, so that's in effect 1 upon 2. But it's 1 upon 2 times this value of L. Well, this value for L is 2 to the power of 2. Okay, so that's going to be 1 upon 2 times 4, which is equal to 2, which is just our value here. So this thing here, mx, L, is just the same as this big mx here, and it works out to be this value of 2. Okay, so given that, we can then simplify this equation. We could take out the common factor of L. So we've got the common factor of L. We can keep the m, and we can also note that this exponent value, well, the exponent value is nothing other than the exponent value here, and we just interpret it in terms of a decimal, a binary number. That's what we do whenever we generate the normal floating point number. We interpret this number here in terms of 2 raised to this exponent. So it means that we can just replace this e here, the exponent, with the value for the exponent. So the value for the exponent we know is going to be the e plus b. Okay, so it's going to be the actual exponent plus the bias. Okay, so it's going to be an actual exponent plus the bias will give us the actual value that we're going to put in here. So it means that we can rewrite this ix is equal to L e plus b plus m. Now, whenever we do our 32-bit number, the value for our L is going to be 2 to the 23, because we've got 23 bits for the mantissa. Now, the bias in our 16-bit or 32-bit representation is a number 127. So again, in the 16-bit, these values are going to be different, but we will look at a 16-bit example later on. So the most important thing to get out of this so far is that we've got this little equation here, ix equals L e plus b plus m, and this is what we'll call equation 1, and this converts a floating point decimal to the integer representation, and it converts it in terms of these values here, the e, the b and the m, and also this value of L. So it's a nice way of connecting this number here, which is kind of very random, but it connects this random number to the actual floating point representation. Now let's look at an actual example, because from this example you'll see it actually working. So we know that if we're going to represent the number 4 in our floating point number, then we are going to end up with a number which is this number here, whenever we interpret it as an integer. And we know that we should be able to generate this number using this equation. So let's put the values in for the equation. If it's a number 4, they're going to have the L, well, it's a 32-bit representation, so it's going to be 2 to the 23. And then when we open up the brackets, we're going to have our value for our exponent. So our exponent is 2, because we're going to have the value of 4 is the same as 2 raised to the power of 2. So the exponent is a value of 2. And then we're going to have to add in the value for our m. But what we'll do is we'll just take the m and the l and we'll take them out as separate, okay? So we're going to, in effect, have l, m times l, okay? So we've got l times that plus that, and we're going to have m times l. Now in this instance here, the example I gave you is a simple one, okay? All of the values here for the mantissa are 0, okay? So we're going to actually have 0 times 2 to the 23, but it would still work out if we had any 1 within here as well, okay? So we're going to have 2 to the 23 times 129, which is equal to 108,213,0432, which is just this number here. So this is equation 1, and I think that's enough for this video. It's quite detailed actually, and whenever I try to start describing it in English talking, it does actually take a little bit of time. So we'll continue with this on the next video, and we'll see how we're able to use this equation and some other neat mathematics in order to generate this fast inverse square root. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.